we already know there are three kinds of magmas. There's granitic magma and there's andesitic magma. Those were being formed now at the zones of subduction. And then there was the basaltic magma was being formed at all those rift zones. Those are the three types of magma. So here's what I want you to consider. Looking at that chart again, what I want you to do is picture the basaltic magma at the top, the granitic magma at the bottom, and the andesitic magma in between. Now what is that saying? That's saying that out of the basaltic magma, the only minerals you can possibly get are the minerals on top of Bowen's crystallization series, namely olivine, augite, and anorthite, those kind of minerals. That's what's going to precipitate out from a basaltic magma. That's what the rock basalt is made of. Note, there's no quartz in there. There's no orthoclase in there. Why? It doesn't have the stuff to do it. Now let's go down to the bottom. Let's say we take a granitic magma and you cool it down. What we're saying is that out of the granitic magma, you are going to get quartz, you're going to get orthoclase, you're going to get muscovite, and you may actually pick up a little biotite over there and maybe a little bit of that albite, because those minerals are the stuff to make them are in the granitic magma. But note, you're not going to get any olivine, you're not going to get any anorthite, you're not going to get augite. Why? You don't have the stuff in it to make those things. And then, of course, the intermediate, or the andesitic stuff, they're going to make the minerals in between. So the point is that each of these magmas we've been talking about, there's a limitation as to the kind of things that they will produce. There's only certain minerals will precipitate out, and all you have to do now is look at this chart and see which minerals will precipitate out of each of the three magmas. Now, there are two other words I want to put into this little diagram. One of them is the word mafic, the other is the word felsic. Now, they look like nonsense words, but they really aren't, and I won't bore you with where they come from. But I want you to position mafic at the top of our list, felsic at the bottom, and some people like to put intermediate in the middle. Now here's the beauty of these three words. Let's take mafic. Mafic simply means you're dealing with things at the top of the list. So for example, if I said, I'm thinking of some mafic minerals, what do you think they are? Well, they're probably going to be olivine, anorthite, augite, but they're sure not going to be quartz and orthoclase, because you see they're down at the bottom. So in other words, that one word, mafic, tells me what minerals we're talking about. Question? The mafic tells me what else? Well, it tells me we're talking about a basaltic magma. So just that word alone tells you what magma we're talking about, and it tells you what minerals we're talking about. Felsic, on the other hand, says you're dealing with things at the bottom of the list. You're dealing with things in terms of minerals like orthoclase, like quartz, like muscovite, but you're not dealing with olivine. So you see, those are the kind of minerals that felsic represents. What's the felsic magma? It's the granitic magma. So if you're talking about magmas, you're talking granitic. Intermediate, of course, obviously is the andesitic magma and the minerals that come from it. So just using those words right off the bat, you can tell anything you want to know about the kind of minerals and the kind of magmas that you're dealing with. So those are very, very handy words we use all the time in describing these minerals and these igneous rocks. Now let me show you something that's wrong with that chart that we've just described, where we started off with olivine at the top and ended up with quartz at the bottom. Remember now, this is temperature from high to low. That's a temperature on the side. So picture now coming down across that with your hand. As you come down across that with your hand, the first mineral that appears out from your hand, olivine. Then you come down a little bit further, anorthite. Come down a little further, augite. You see, every time you come down, a new mineral appears. Now, basically what that's saying, if you just go over to the side where the temperature is, that's saying that those individual minerals have specific freezing points. That's what that's saying, specific freezing points. Is there anything wrong with that? Well, there's nothing wrong with that, but the problem is they will have specific freezing points if the composition and the crystal structure is fixed. But the problem is if you look at the formulas for some of these minerals, and let's just look at the one for olivine because it's the easiest one to remember. Olivine is iron magnesium silicate. A chemist would write the iron and magnesium in brackets and then silicate. What does that say? That's a chemist's way of saying that you can have iron olivine, you can have magnesium olivine, You can have an olivine that's 50-50 iron and magnesium. You can have one that's 75%, 25% iron and magnesium. In other words, the range of compositions. Well, that's going to affect the physical properties. So the idea is that olivine does not have a specific temperature at which it crystallizes. It crystallizes out over a range of temperatures reflecting that change in composition. And if you look at all the other formulas, with the exception of quartz now, all of them are like that. Look at hornblende, for example. There are a bunch of little brackets in hornblende. It has a tremendous variation in composition, which means it is going to precipitate out over a range of temperatures. That chart really didn't show it. But I had another chart that I put together, and this chart is supposed to take that into account. Now, if you look at this next chart, the center of the diagram shows the minerals again. But if you look at it, what that shows is that it reflects the range now of temperatures at which these things precipitate. Again, remember, high temperatures at the top, low temperature at the bottom. If you look at olivine, for example, it shows olivine sort of slanting down from the upper left-hand quarter to the lower right. That's telling me that it actually precipitates out over a range of temperatures. And if you look at the rest of the minerals, they all do the same thing. So this little chart now actually reflects the range of temperatures, reflecting the range of compositions of these minerals, something the first chart didn't show. Now, remember now again, Bowen said this isn't perfect. There are things going on that he didn't understand, and here's something that he was talking about. If you look at the chart, quartz also has a range of temperatures over which it precipitates out. It shouldn't have a range. Quartz is always silicon dioxide. The composition never changes. The structure never changes. And yet, here you have this quartz on this diagram precipitating out over a range of temperatures. Why? I don't know. Bowen didn't either, so I don't feel too badly if Bowen didn't know. So this is the part where we say it's too complicated. There's things going on that we don't understand. But nevertheless, if you look at that chart now, that chart reflects better how these things precipitate out. Now, if you were to take your hand and come down across the chart, watching the minerals that precipitate out, the important thing is you see the range of temperatures, but most importantly, you see that at any temperature, you can have multiple minerals precipitating. For example, if you come down the chart, you can see, for example, you can have augite and a little bit of anorthite coming out simultaneously. You couldn't see that before. So anyway, that's a little bit difference in the chart now. We'll get back to that. Now, in the chart, I also have on one side coarse-grained, other side fine-grained. So the coarse-grained would be those rocks that form basically from magmas by slow cooling. On the other side, we have the fine grains, which would be the fast-cooling lavas and things like that. And what I've done, I sort of bold-faced some of the rock names. Peridotite, basalt, granitic rocks, andesite. Those are highlighted. And why? Because these are the rocks that we've been talking about most in our discussion so far. But here's the way the chart works. Let's say we take peridotite. The way the chart works, if you want to know what mineral composition could you expect in peridotite, here's all you do. You simply draw a line horizontally from peridotite across the mineral chart and look at the fields that the line crosses through. Whatever mineral fields that it goes through, those are the minerals that you'd expect in peridotite. Note, you can go across there and be totally within the olivine field. Why? Well, there are olivines. I mean, peridotites, they're 100% olivine. But note, you can have a little bit, perhaps, a little bit of anorthite in there, a little bit of mixture, but it says peridotite is mostly made up of olivine. Let's drop down, pick up basalt. Again, draw the line opposite basalt across the chart. Well, if you did that, what it would show would be, well, you can have some plagioclase feldspar in there, probably the calcic variety. You can probably have some hornblende now in there. And you will have very little olivine because you're outside that field now. Maybe a little bit of augite, but you're getting close to the end of that one too. So just going across there, you can see what the mineral composition is of basalt. But note, if you go all the way across to the other end of the line, there's another mineral on the coarse-grained side called gabbro. Now, what's the significance of that? Well, the significance of that is that gabbro and basalt have the very same compositions. What's the difference? One's coarse-grained, one's fine-grained. Well, how can you do that? Well, again, here's all I want you to do. Picture that oceanic ridge. Picture that basaltic magma down there that's coming up to the oceanic ridge to form the new oceanic crust, the basaltic crust. We call that a basaltic magma because we want to emphasize the fact that it's going to come to the surface to produce basalt. But note, on the way up, if it's sort of solidified on the way up, to form what? Note, to form the lower portion of the lithosphere. In other words, when you're creating out there at that oceanic ridge, isn't just the basaltic oceanic crust, you're producing the entire oceanic lithosphere. The top layer is, in fact, basalt because it's solidifying in contact with the water. But note the bottom, same magma now, is crystallizing at depth to form the lower portion of the lithosphere. That's gabbro. That's the whole point. And so they're both the same composition. They simply developed one on the surface, the other at depth. So that's the significance of, say, gabbro and basalt. Now, if you go down to the bottom, let's talk about granitic rocks and rhyolite. Granitic rocks, these, of course, are the ones down there. You look to see what it's made of. Orthoclase feldspar, lots and lots of it. A lot of quartz, there it is down there. Plagioclase feldspar, yes, it's going to be that stuff down there, the albite. And a little bit, perhaps, of biotite. And think of your kitchen table or whatever your counters. That's what granites are made of. Now, if you look over the other side, there's a mineral over there called rhyolite. Now, it's not really bold-faced because rhyolite would be the fine-grained equivalent for granites. Well, remember, the thing is that granites now are the stickiest kind of magmas there are, very high viscosity. They really don't come to the surface very often. But when they do, we're going to find out in our little chapter or discussion of volcanic eruptions, they're going to have an eruption like the which has never been seen in historic time. That stuff is going to be blasted into the air, break into tiny little pieces, which are going to solidify very, very fast, fine-grained, you see, and is going to fall as rhyolite. Well, if you want to see a place like that, the place you want to go is Yellowstone Park. If you go to Yellowstone Park, all the rocks that you see in Yellowstone Park would be the fine-grained equivalent to the granitic magma that blew out to the surface. Well, the first time was 2 million years ago. The second time was 1 million years ago. The third time was about 600,000 years ago, and it's getting ready to do it again. So anyway, that's what the chart shows that. So here we have now a chart. You see how the mineral part works. You see how the rock types work, how you can determine what the mineral composition of any rock is by simply going through the fields on the chart. But also in this chart again, note I also have where you'd expect to find these things. Peridotite. On the chart it says peridotite. That's the stuff of which the mantle is made. So that's on your chart. So that's the reminder of where that comes from. Basalt, okay? Basalt, this is oceanic crust, so that's marked on the chart. Gabbro over there, that's the lower part of the oceanic lithosphere, so that's on the chart. Andesite, those are your arc volcanoes. Those of your arc volcanoes, be they continental arc like the Andes or island arc like the Aleutian Islands, that's on your chart. The one down at the bottom, the granitic rocks, granite and granodiorite, that basically is your the continental crust. So that's on the chart. And so now we have a chart that has just about everything we need to know about the composition of the igneous rocks and the classification scheme all on one chart. So much for igneous rocks. We're going to get on now to sedimentary rocks, which is probably going to be a little bit more, shall I say, these are the rocks you're going to see most often. You want to see igneous rocks, right now you'd have to go to the cores of mountains, things like that. But the sedimentary rocks we're going to see around us most of where we go because they cover 75% of the land. So the next one is going to be sedimentary rocks.